all ideal gases obey an equation of state known as ideal gas law, and the ideal gas law is given by PV equals N R T. So here the P indicates absolute pressure, V indicates the volume, N indicates the number of moles, R indicates universal gas constant, and this R is going to have different values based on the value of P, V, N, and T. T indicates the temperature. And this ideal gas law is formed or derived using two other laws, namely Charles' law and Boyle's law. Now, to derive the equation of state for ideal gas, we need to understand the Boyle's law and Charles' law. So, let's start with Boyle's law. This graph indicates pressure and volume diagram, and these curves here, they are all isotherms or constant temperature lines. Boyle's law states that the volume of a given mass of a perfect gas varies inversely as the absolute pressure at constant temperature. At constant temperature, we can say PV is equal to a constant, or we can write it as P1 V1 is equal to P2 V2 if 1 and 2 are the two different states. To understand Charles' law, we can take a look at this diagram. So this is a temperature volume diagram, and these lines are isobars or constant pressure lines. Charles' law states that if any gas is heated at constant pressure, its volume changes directly as its absolute temperature T. So we can say at constant pressure V by T is equal to a constant, or if there are two states, state 1 and 2, we can write V1 by T1 is equal to V2 by T2. To derive the equation of state for ideal gas, a unit mass of gas is considered, and this gas is changing its state from 1 to 2 dash at constant pressure and 2 dash to 2 at constant temperature. So this is going to be a constant pressure process. So dP is equal to 0, and this curve or isotherm is a constant temperature process. So 1 to 2 dash is constant pressure process, and 2 dash to 2 is constant temperature process. The notations are the same, where P is the pressure and V here is the specific volume, and T is the temperature. For the process 1 to 2 prime, since it is a constant pressure process, we can apply Charles' law, and we can write it as V1 by T1 is equal to V2 prime by T2 prime. And since 2 prime to 2 is a constant temperature process, T2 prime is equal to T2. So we can rewrite this expression as V2 prime is equal to V1 T2 divided by T1, and we are going to call this equation as equation 1. Similarly, for process 2 prime to 2, which is a constant temperature process, we can apply Boyle's law. Applying Boyle's law, we can get P2 V2 is equal to P2 prime V2 prime. And we can see that process 1 to 2 prime is a constant pressure process. We can say P1 is equal to P2 prime. We can rewrite the expression as V2 prime is equal to P2 V2 divided by P1. And we are going to call this equation as equation 2. By applying Charles' law and Boyle's law to the given state change, we have equation 1 and 2. So now we can equate the equations 1 and 2 and we can write an expression V1 T2 by T1 is equal to P2 V2 divided by P1. So we can rearrange this equation and we can write it as V1 by T1 is equal to P2 V2 divided by T2 P1, or we can write it as P1 V1 by T1 is equal to P2 V2 by T2, or we can say PV by T is a constant, and this constant is going to be given with a notation R. So we can write it as PV by T is equal to R specific. This R is specific gas constant. When we rearrange this, we can get the equation of state, which is PV equal to R specific into T. For a gas of mkg occupying a volume V meter cube, we can rewrite this equation as PV equals M R specific T. If the mass is equal to the molecular weight of the gas, so we can rewrite this expression as P V0 is equal to uppercase M, which is molecular weight, into R specific into T. So here the volume V0 is the molar volume and the M is the molecular weight of the gas. So according to Avogadro's law, the molar volume is the same for all ideal gases if measured at the same temperature and pressure. Therefore, we can write M R specific is equal to a constant which is also called as universal gas constant, and the value of R is 3143 kilojoule per kilogram mole Kelvin. So now we can rewrite the expression as PV0 is equal to RT. If the gas contains n moles, then we can rewrite the expression as PV is equal to NRT. Since molar volume V0 is equal to the total volume divided by number of moles. So the equation of state for ideal gas that occupies n number of moles is PV equals nRT.